Hi guys, I'm Luke Bennick with 3Helix. In this short video I want to talk to you guys about how you can use collagen hybridizing peptides to visualize mechanical damage in tissues. But before we get started, I'll give you a little bit of background on collagen and our collagen hybridizing peptides. So to start, the collagen molecule, or collagen fibers, are based on a hierarchical organization where you have a collagen fiber made up of collagen fibril, which is then composed up of a collagen molecule. Now the collagen molecule itself is actually a form of a triple helix, and it is made up of 3 individual alpha chains. You could think of this as a rope where you have 3 pieces of twine and they interact together to form a rope-like structure, and this rope is much stronger and sturdier than each individual piece of twine. So in nature you have an intact collagen triple helix, but when it gets damaged, such as mechanical overloading, the collagen triple helix begins to unwind and unfold. Now this is important because this is how our collagen hybridizing peptides are able to target regions of damaged collagen. So if you take this is a collagen fiber, and it is getting damaged by MMPs in this example. However, you can think of it as a mechanical damage as well, and basically you get these single-stranded collagen fibers that are exposed to the microenvironment. Now we designed our CHP based on a glycine, proline, and hydroxyproline repeating peptide. Now this is important because this specific sequence has the highest propensity to refold into a collagen triple helix. That means if we apply it to tissues, it will target the CHP, or the CHPs will target the collagen based on that alpha strand that we talked about in the previous slide. So what we were able to do is we were able to attach fluorescent probes or biotin labels onto our CHPs, and then when we apply it to the tissue or gelatin substrates, these CHPs will then fold back into a collagen triple helix with either 2 collagen strands or 2 CHPs to 1 collagen strand. So taking it back to our original example, we have an intact CHP or intact collagen. Once it's mechanically damaged, this collagen triple helix begins to unfold, and then our much shorter collagen peptide is able to sneak in and refold that collagen triple helix, and because it has a fluorescent probe on it, we are able to visualize regions where there's high amounts of collagen damage or collagen turnover. So in the terms of mechanically damaged tissues, I'm going to take you on a few examples of rat tail tendons, and this is done in our Nature Communication paper, where we tested several rat tail tendon fascicles, and we did multiple stress-strain relations. And as you can see here, basically anything within the linear region is not causing permanent structural damage, which is to the left of this dotted line. And then once you go past the linearity part, this is where you start to see permanent structural damage within collagen fibers. And basically what we were able to do is we took a rat tail fascicle and we put it in between 2 metal clamps, and then we stretched this fascicle out to between 0 and 15% strain. And what you can see here on figure B is several different strain levels. We had 5%, 10.5%, and even 15% strain. The white block arrows indicate where the clamps were held. So on the right hand side, you don't have much mechanical strain because that's where the tissues were clamped down and the strain was not produced in those regions. However, in this middle region on the loop section, you see as you increase the strain, you see increase in CHP fluorescence signal. Now this indicates that there's higher amount of damage, and this at 15% and at 10.5%, you see much higher signal fluorescence than you do at 5%. And it is known in the field of tissue biomechanics that the transition from this linear region over to this non-linear region causes structural damage, and it's right around 6 to 8%. So we see, under that percentage at 5%, you see low levels of CHP, but over it, you start to see higher levels of CHP intensity. And to show that this CHP intensity was not just surface level, like only on top of the fascicles and the tendons, we actually did second harmonic generation imaging, and we compared it with 2 photon excitation fluorescence. So if you take a look at panel A, we did Z stacking, and you can see that there is a fluorescence signal all the way through up to 80 microns thick. And when we compare the signal when we compare the 2-photon excitation fluorescence to just SHG signal, you actually start to see that the damage within the collagen fibers is non-homogeneous, and you see regions where there's higher amounts of collagen damage compared to the rest, and you really don't get that distinction when you look at an SHG image alone. And then this bottom panel in panel C, we show the SHG signal, and then this region is stained with CHPs. However, it was not strained, so you can see again that you only see signal fluorescence when there's damage caused to the molecule, and in this example it was caused mechanically by straining the rat tail fascicle. The other thing I'd like to point out is when you compare CHP staining with common antibody staining, you actually see much better indication of where damage is from the CHPs than you do with the antibody. So we took 2 separate samples. On the left-hand side, this left-hand column, the rat tail fascicle did not undergo any type of mechanical strain, and we stained it with the CHP and with the type 1 antibody. You can see with the collagen type 1 antibody, you see a nice red color. And then when we compare that, the healthy tissue, to a 15% strained tissue, you see roughly the same amount of fluorescence in the antibody. However, when you look at the CHP, which only targets damaged collagen, you see in the healthy tissue there's no fluorescence, but in the 15% damaged tissue you see a high level of fluorescence. So this indicates that the collagen 1 antibody cannot distinguish areas of mechanically damaged collagen, while CHPs can really easily make that distinction. Another example with this same rat tail fascicle is we combined our collagen hybridizing peptide with a commercially available gold nanoparticle, and we evaluated several different tissues. We evaluated at 12% strain, and then we evaluated fascicles that were completely unstrained. So on the left-hand side is you see a native image, and then on the right-hand side of all of these you see our images where we highlighted where the gold nanoparticles were in these yellow dots. Now these sections of white outlines indicate where there's still sections within the collagen, within the fascicle, that there are still this nice collagen D banding pattern. So in this unstrained rat tail fascicle, you see the banding pattern is found throughout the sample. When it's completely damaged, or not completely damaged, but when it's exposed to a high amount of strain, you see lower and lower levels of regions with this nice banding pattern. So in this top section, we did a 12% strain model with our targeted CHPs attached to gold nanoparticles. In the bottom, we have a healthy tissue section, again stained with CHPs attached to gold nanoparticles, but because the collagen is intact, you see very low amount of collagen binding, or CHP binding to the collagen. And C was our control sample, where we had a highly strained, highly damaged fascicle, and we stained it with a scrambled control sequence which does not bind. So between the 3 of these, you can see that there is low level of nonspecific binding with the collagen hybridizing peptide, and that it only binds to regions where there's high collagen damage. So these banded patterns are still intact. And when we actually quantified this using the area that the gold nanoparticle takes up within the image, we see that there is a higher CHP gold nanoparticle density within the 12% strain model when compared it to the undamaged molecule, and when we compared it to our negative control in panel C, which cannot bind to denatured collagen. We took it a step further, and when we evaluated the gold nanoparticle density within these banded regions, within these white outlined regions, you saw that most of the CHPs tended to bind outside these regions where there is a higher amount of damaged collagen. So in these examples, this was done in a highly specific manner where we mechanically strained these tissues on purpose, where in the next example I'm going to talk about, it is actually a myocardial infarction model. So it's a heart attack, and we can actually visualize the amount of mechanically overloaded tissues from a heart attack within a mouse heart tissue. So again, we used a biotin CHP molecule, and you can see in a normal mouse heart, there's no binding with CHPs. However, when we induce a myocardial infarction or a heart attack, 3 days post and evaluated it all the way up to 14 days post heart attack, you start to see areas where there's collagen, CHP binding to collagen remodeling, with the highest amount of remodeling occurring 7 days after the heart attack. And again, heart attack is made by a blockage of the arteries, and it causes a mechanical overloading, and this mechanical overloading gets distributed through surrounding tissues. And when we compared this biotin CHP staining to the CD68 marker, which is a common macrophage marker, and macrophages are typically in the area to help with wound resolution and to clean up debris and different fragments after injury. And when you take a close-up of this region here with the CHP stained in yellow, the CD68 stained in green, you start to see an overlap where there's high levels of CD68 macrophages. There's also high levels of biotin CHP binding, indicating that it does follow where the damage is happening. So, in conclusion, CHPs can extinguish collagen that has been mechanically damaged, which can be useful in tissue engineering for evaluating torn tendons or ligaments after injury, or for even determining the mechanical properties of a scaffold. So this would be ideal for monitoring for damage resolution or for wound healing. The other thing we were able to show is that CHP fluorescent intensity correlates with regions that have more damage to the collagen. This was seen in the rat tail fascicle experiments, where you saw increasing strain shows increasing CHP signal, and that CHP intensity was not confined to damaged collagen on the surface, but they were actually able to permeate and stain throughout the tissue sample. And lastly, we showed that CHPs can be conjugated onto commercially available gold nanoparticles, so you can use it in TEM imaging. And again, these CHP gold nanoparticles target regions with disrupted banding patterns or the damaged areas within the rat tail fascicle. So again, my name is Luke Bennick. If you have any questions whatsoever, please feel free to contact me. And I also wanted to introduce you to other members of our team. Helen King is in charge of ordering and shipping CHPs for you. And if you have any interesting applications or have ideas for partnerships, please feel free to contact Dr. Mike Kirkness of our business development team, because we are always looking for new applications. And take a look at our other application videos. It shows other disease states that CHPs might be helpful for. And also keep an eye out for our publication page. It's always updated when new publications are published. Thank you.